Welcome to my thesis presentation. This was, as you can see from the title, a Master's in Data Science and Business Analytics capstone project, which was titled Optimizing Carbon Emissions in Freight Vehicles Using Data Analytics. I'd like to thank both my supervisor and second marker for their insightful help and general overall guidance throughout the course of this project. So now let's get started. Okay, so this project was split into 6 different chapters. The first being introduction, which looked at understanding key findings that were instrumental in propelling the continuity of this project. Problem statement was basically understanding what this project is meant to solve. Research questions, these are questions related to the problem statement that are being looked at in a way that I would need to find literature and see how these questions can be solved using scientific means. Aims and objectives looks at what are the goals that this project was aimed at solving, and understanding the actual science behind them. Scope of the research are basically a set of limitations or boundaries that govern this project. Second chapter is a literature review, which is state-of-the-art literature review, which looks at various findings from different authors and understanding how these relate to the first chapter in terms of solving the research questions. How do these meet the aims and objectives, and also should be within the scope of this project. Okay, the third chapter is a methodology, which looked at the project design and data mining pipeline. The project design looks at how this project was created, built to solve the questions that were raised in the introductory part, and how does this overall fit within the problem statement resolution. Data mining pipeline looks at the OETL process, extract, translate, load of data. So that's staging the data prior to machine learning modeling. And then in the fourth chapter, we have findings and results, which are experimentations and their outcomes. Conclusions is a synthesis of the findings. It will interpret the results and illustrate how these objectives were met within the context of what was devised in the first chapter. This last chapter is the discussions. It looks at 3 different aspects: contributions, which are literally just the significance of the findings, limitations of this study, as well as areas of future research. So what was found, or what would have been done better within the context of this project. All these are articulated in this 6th chapter. Okay, let's get started. We'll first look at understanding the fact that transportation accounts for about 14% of total global emissions, and is therefore ranked as one of the major contributors to greenhouse gas emissions. Another finding is that 78% of transportation emissions stem from freight vehicles. Now, this is quite monumental because we've got a leading supply demand, supply chain network. Thanks to globalization and digitization, we can literally just buy things online, and you've got items shipped to whichever part of the world you live in. Most of the time, we're using freight, road freight vehicles. That's if it's inland travel. If it's sea, we're using, of course, ships and whatnot. If it's air, you're using planes. But in the context of this study, it's only looking at terrestrial vehicles. Okay, then the other part that was considered was the fact that machine learning is a tool that's being used to optimize climate change consequences from ICVs, or internal combustion engines. This was a major finding by Ronek. I think his article is quite pristine. It was entitled Tackling Climate Change Using Machine Learning. I really enjoyed this article. Okay, let's forge ahead. We'll look at the problem statement. So thing is, land transportation leads to high carbon emissions, right? And this has a direct correlation with climate change. So now this was the end point for this study, in that there's this problem which is human caused, and we need to find better means to understanding how to, for the moment, minimize or optimize carbon emissions that are being generated from these fossil fuel burning vehicles. So another essential finding here is that emissions from freighting of goods is categorized as a total emissions and is not directly controlled. Now this is quite monumental. You can have companies setting up KPIs, key performance indicators, but do not instinctively create a sort of measurable, tangible KPI for carbon emissions, the carbon footprint, whether be it waste of in-house material or transportation or different aspects of the supply chain or and operations that they do, logistics and transportation, that is. Okay, so now we look at the research questions. There are three of them. The first one is, in what ways does data analytics through vehicle routing problem lead to a reduction in carbon emissions? That's in the context of fuel-based vehicles. The second question is, in which vehicle routing algorithms offer the best optimization outcomes? Last question is literally just understanding the difference between enhanced dynamic and traditional vehicle routing, and which one of these two will allow for better carbon emission minimization. Okay, and then the research and objectives is are directly correlated with the questions that were asked. So with the first one is exploring how data analytics is applied in solving carbon emission issues caused by ICVs. Second question is comparing the reduction in carbon emissions when dynamic routing problem is applied to a non-dynamic routing problem. So now this question just literally, this objective literally just looks at how comparable carbon emission optimization means to non-optimized transportation means. So route optimization to non-route optimizations. What's the difference in carbon emissions? This is something that we'll solve. Then the last objective was to determine the most environmentally cost-effective predictive model using route optimization in a given supply chain. So that in itself is quite subjective. We'll see how this project resolve this. Okay, scope of the research fell into three different aspects. The first part is it's only limiting to carbon emissions, not the entire footprint of greenhouse gas emissions from cars, and is only measured for cars sold in France in 2015, as we'll see from the dataset. So the second part is European Union transportation regulations, which France is part of, were considered, and therefore this is the restriction of this research. The last part is analysis of carbon emissions is only limited to two fuel types, petrol and diesel vehicles. We'll see how feature engineering led to just having two different fuel subcategories instead of the whole fleet of, I think there are about 13 or 16. Okay, so now when we look at the literature review, there are four different aspects that were found here. The first part is fuel consumption factors, which are related with whether it's an urban or city route or a highway, with city incurring higher fuel consumption due to traffic congestion and planned velocities, as well as undesired engine starts and stops. Highway relatively incurs less fuel consumptions or carbon emissions compared to city routes due to these factors. Okay, so now we also look at freight optimization solutions. Now classical computing through mathematical modeling has provided sufficient evidence for optimizing CO2 emissions in transportation. Okay, but the problem is that it suffers from non-robustness and require domain expertise. So for someone to instinctively create optimal real-world solution using mathematical modeling, they'll need to be really knowledgeable in terms of hyperparameter tuning, literally tuning that model for the problem that's been faced. So in which case, most of the time, it's not really applicable to real world due to the complexities, especially in transportation, multimodal factors, environmental factors. Mathematical modeling does not really apply well. Okay, we also look at sustainable freight transportation. From the literature, there's somehow synchromodal transportation facilitates efficiency without compromising on sustainability. So other approaches will literally just look at supply chain network design as well as truck platooning. We'll see how AI machine learning is applied to modern solutions in truck platooning. Okay, then the last part looked at the predictive modeling, which is the machine learning part. We've got intelligent transportation systems, which are being applied using, if I may, classical machine learning as well as deep learning algorithms in traffic flow predictions, thereby limiting carbon emissions from internal combustion vehicles. Okay, we'll go to the methodology. It's split into five categories. First part is, the first search for the dataset was rather random. It looked at one key aspect with the dataset being, of course, the multimodal dataset with transportation as well as having the CO2 feature. So now this was done through different sources, Figshare, Cargo, as well as Mendeley and Google datasets were all skimmed through to find a particular dataset. Second part is the search criterion. Three search criterions that were set. The first part is the number of instances was set to 20k. The other was 13 features. Then having carbon emission variables quite important for this search. Then the third part is carbon emissions from a dataset which was for cars sold in 2015. And then we have the implementation part, which was set into two categories. The first part was creating a synthetic dataset, leveraging the predictive power of city and highway features. So now this in itself meant the prediction will be based on finding the difference between carbon emissions from city and highway emissions, which is shown in the CO2 predictions in the fifth part. Okay, so now we look at the metadata for the dataset that was found. So now this dataset was in French. It was transcribed to English. Lots of unnecessary variables that were included in here. Most of them administrative that had little to no importance or significance to this study and were therefore dropped. Feature engineering. The main feature engineering that was done was using the fuel feature, which had about 16 subcategories of different fuel types, from biofuels to type of hybridization mode of cars. So now all these were dropped because they had little instances within the dataset, with fuel and diesel, with petrol and diesel vehicles constituting about 91% of the total number of counts in this particular feature. So therefore the others were dropped and only these two were kept. So look at the evaluation metrics. We used three different evaluation metrics for different purposes. We have the root square error, which looked at relative measure of fit. So how well does the data fit regression? So now this was done using a scale of 0 to 1 as it is, with 1 being a perfect fit, which in the real world does not really happen because there's no data that fits a model 100%. Then the second evaluation matrix was the mean square error, which looks at the estimator measures and basically just showing that having a low score in MSE leads to a good model, as the case with the root mean square error. It looks at the standard deviation of residues. So the lower the RMSE, the better the model is. So now we look at the final modeling. Okay, first part that was done was, of course, data pre-processing, which looked at feature selection, as I earlier alluded to, deleted or dropped unnecessary predictors. Variable imputation was done through mean imputation because most of the data that was found here were numeric. Needless to say that For fuel, I had to do one-hot encoding to transform categorical data into numeric representation, dummy data. Outlier treatment involved quantile percentile from 25 to 75%, so the data was kind of trimmed through that to get rid of any noticeable outliers. Normalization and standardization was done through log transformation and standardization. Standards scalar using scikit-learn library. I think I use pandas for log transformation. And then one of the crucial points to do with regression modeling is understanding the linearity and assumptions. And this involved understanding normality, distribution of the data, how well are these residues distributed? Are they normally distributed? So this was done. Autocorrection was checked. Homodystacity was also checked, as well as multicollinearity. Goodness of fit measure was done through a few simple linear regression models, and this literally just showed whether this model was fit for purpose or not. Okay, and then we look at the models that were done. 3 different models with regularized linear regression constituting elastinet, ridge regression, and lasso models. So now all these were done in accordance to the findings that were done. These linear regression models have different penalization or loss functions with L1, L2, and with elastinet constitution of both of these penalization. An artificial neural network model was done, and a wider artificial neural network was done in the form of a deep neural network. As I alluded to earlier on, 3 different metrics were used to compare the models. Synthetic dataset, as you can see, city carbon emission prediction and highway carbon emission prediction datasets were created. In the city, I had to drop the highway prediction, and in the highway, I had to drop the city prediction feature. And one other feature that was dropped due to high multicollinearity was the mean weight, as it highly correlated with the max weight feature in this dataset. It was almost a 1-to-1 ratio, which would have created some a lower prediction score for the model. Model evaluation, okay, this was done with a 20 to 80% split in the test and trained data with out-of-bag validation and holdout using k-fold cross validation. This was a 10-fold cross validation. Okay, so now the difference was found, city and highway predictions, and this was saved to a file, as we'll see. Okay, so now we go to the results, goodness of fit results. So now this just shows how well this data is fit in the model. So you can see that AdaBoost, linear regression, ridge, lasso, support vector machine, RBF, all performed relatively well with the goodness of fit measure. They're all above 96%. I can safely say this shows that the data kind of fits the regression modeling. Okay, so now for the final modeling, this was done in, as I spoke about, 3 different models with regularized linear regression taking up the last performing 3 models, elastinet, ridge, and lasso. These performed the worst, followed by artificial neural network, and deep neural network had high scores in everything. It had the lowest MSE and the lowest RMSE and the highest R2 in both the highway and city route prediction datasets. So now this just shows how well these models performed. From the you can see the ranking. The first one is deep neural network, followed by artificial neural network, elastinet, ridge, and lasso. So now from the findings, once I subtracted city from highway mileage, the variation was plus or minus 0.01, which is not so significant, but I think once you multiply this by the time factor and the number factor, it becomes quite significant in understanding how much carbon emissions would be saved using a predictive model that accommodates for optimizing these emissions. You can see from the city and highway predictions, the model scored well in both cases, with a few variations because of the difference in predictors. And yeah, this shows that the model lacks complexity and is therefore fit for purpose. Okay, so now when we look at the final prediction, we'll look at out of bag predictions and the final predictions. You can see the patterns kind of marry. They're almost the same but different, because different data points were used for out of bag from final predictions. Therefore, it's different. So this in itself just shows the non-complexity or non-bias in terms of the modeling that was done. It's not biased towards the data. You can see the out of bag and final prediction scores. The results are different because different data points were used, but then again the deviation is not so much. So one thing you can notice if you look at the final predictions is got positive and negative scores, with positive being savings and negative being the opposite of savings, meaning city route incurred less carbon emissions than highway due to the factors that were beyond the control of this project. So therefore, you can say this is a realistic kind of approach to tackling the problem. Okay, so we look at the discussions that were found. As you can see from the previous slides, there was rather inconsistency in the results due to the factors that were devised and found. So one is driver behavior, which is something that is not controlled. Speed, time, and as well as weight and climatic conditions. All these are factors that influence the results. So in terms of modeling, regularized ridge regression models performed quite different despite the weight penalization functions. Artificial neural network performed second best, with deep neural network performing the best, which shows that it can handle quite complex multimodal problems with ease, especially with the proficient hyperparameter tuning. Okay, so now we look at the contributions of this study, or understanding the key importance of this study. So this study looks at implementation approaches that encompassed intelligent transportation within the last 5 years. So also reflecting on what challenges sustainability in mobility are being done in terms of applying real world solutions using machine learning, artificial intelligence to optimize carbon emissions. So the first part is understanding that deep neural network performs well in understanding multivariate complexities within city and highway road usage. Now, this does not only go within the scope of terrestrial vehicle route optimization. It can be using air freight, it can be using sea freight, or whichever other mode of transportation there is, even manned or unmanned drone delivery, which we'll see, I think, a lot of from 2021 onwards. So the second part is artificial intelligence led freighting, which has different applications in truck platooning, using technology such as LiDAR or light detection and ranging technologies. So this is just creating a fleet of trucks to move in a particular order, looking at environmental factors for optimal delivery, and as well as reduction in energy consumption or fuel consumption, as is the case with autonomous vehicles and electric vehicles as well. So another finding was driving patterns. Patterns effectively affect carbon emissions. Now, this was not controlled within the scope of this dataset, but it's something that's worth noting. The human factor in determining cost-saving initiatives for carbon emissions in freighting or transportation as a whole is quite crucial. So another aspect is mathematical modeling, such as integer programming and or operations research, offer limited solutions that are not quite applicable in real world problems, especially looking at the complexities that were earlier alluded to. Okay, so now we look at the limitations of this study. So the first part is just finding the data set. It was quite tricky. I think I've joined several forums, including ResearchGate, Climate Change, Climate Exchange, I think, ask for a particular data set which is open source, or if I need to sign declaration forms for its usage, I would have, but I didn't find any such data. So now this in itself did not quite impede the outcome of the project. It achieved everything that it set out to, but also generalized sustainability, which was biased with intelligent multimodal transportation, which is something I was looking forward to. So one other restriction that was found is the geo constraint, with it being linked to the French government, and as well as the year of 2015, which is a couple of years back. And the other part is understanding that there was no benchmark for machine learning models. So this project in itself was a novel project. It did not look at what another person did in terms of optimizing or creating the project methodology in a way that I did, and realizing the outcomes that I devised. So another constraint is understanding the data credibility issue that is within the scope of this dataset. Volkswagen was sued by the US government for cheating their emission tests, which I think led to a fine of $2.8 billion. So this is quite monumental. So carbon emissions for VW vehicles, which were included within this dataset, lead to data integrity issues. Another constraint is fuel vehicle limitation, biofuel, compressed natural gas, as well as clean diesel and hybrid vehicles from a number of green vehicles. This was not used. Only petrol and diesel vehicles were used. So this is something that can be perhaps looked at in a future research. Future areas of research, we have an understanding that vehicles are being moved from combustion engines to being motorized. Okay, and we have the recent CES 2021 CES with General Motors project with Bright Drop, as well as Cruise projects for both commercial and personal autonomous electric vehicle mobility, in kind of going towards a smart city environment. Okay, electrification is one of the future areas of research in terms of understanding carbon emissions. While this is being rated as zero carbon emission, this is quite subjective. We need to look at the environmental cost of battery manufacturing, car tear and wear on the road, all that's contributing differently to carbon emissions, as well as the source of power, source of energy. Is it coal based? What sort of energy are these cars recharging from? So that's something that needs to be looked at. So another research area is using clean fuels and understanding how realistic these approach are to carbon emissions. Just how well do these limit carbon emissions? Okay, so another part is, as I earlier alluded to, we've got truck platooning using autonomous vehicles. Now, lots of research in internal combustion engines have tried to incorporate autonomous vehicles, autonomous driving, but in which case it's still leading to carbon emissions, no matter how much the savings are. But these cars are still, producing carbon emissions. So the future is basically just electrification, not even hybridization. It's just electrification that needs to be thought of quite clearly. And definitely there's lots of work that's been done from 2021 onwards. We've got major car manufacturers producing really intelligent vehicles. So now this is the end of my presentation. So thank you very much for paying attention. according to my supervisor, the only question that he came up with was why didn't I come up with a kind of percentage in terms of carbon emission savings within the context of my research. That would have been good to have, but my kind of defense for this was because my data was not credible enough. So scientifically, you need to have data to back up your claims, in which case my data is not really backing me up because it lacks that integrity from that Volkswagen lawsuit and carbon emission cheats. So therefore, I kind of answered the question in that way. So yeah, there goes. So thank you for watching. In my next podcast, I'll showcase the pipeline from my Jupyter notebook of this project and see where I would have done better or what I did better, and just showcase everything. So thank you for watching and have a good day.